Before we get into this talk, immediately following this is an intro to lockpicking in the Lockpicking Village, so check that out. At 3 o'clock is the Fail of Things in the chill out room, so either attend or submit something last minute for that. Later today all the contest ends, so if you are playing Tamper Evident, Deobfuscation, or Capture the Flag, by all means, good luck and get flags. Closing is going to be at 5 in this room, so come back here if you're not already here at 5 to hear more of me talking, I guess. Aside from that, we still have t-shirts available until around 5, so if you want a LayerOne t-shirt, they're available at registration for 20 bucks. We also have recordings of all the talks available from the folks at Media Archives, so they will give you this very snazzy thumb drive, in fact, of all the talks. All the talks cost $40 for the whole shebang. If you want a specific talk, it's $5, and just talk to them outside. Without further ado, we have Ignat with Enforcing Web Security and Privacy with Zero-Knowledge Protocol. So give him a big hand.
Thanks. Hello, everyone. I lost my voice from yesterday. Am I speaking too quiet? No? Yeah? Speak loudly? Okay. It's already on maximum. 1-1. Okay? I don't see my screen now. Thanks for finding strength to come here at this session after lunch on Sunday. I know it's very stressful, but I'm a little bit lucky, so today I would like to talk about zero-knowledge protocols and how can they improve our security and privacy on the network. And before I start introducing you to zero-knowledge protocols, there is a short section, why should we do that? I'm actually lucky because today at 10 a.m. session, Herbert did a very concise presentation of why security is important in medical sector. So I can assure you similar things happen in all other sectors. So basically, you subscribe to many online web services every day, and most of the time you always give away your PII to the service provider. And what happens is service provider always promises you to take all the relevant measures to store it securely, and also service provider promises to give you a secure online experience by forcing you to create a password for your online account, and may be enabled to factor authentication and other stuff. But what happens in reality is that user databases leak, and recent examples is UK medical records leak or Turkish citizenship database leak. Well, PII leaks as well, so because most of the time there is no clear definition of what those relevant measures ought to be, and these end up almost only like administrative or organizational measures without any technical means, especially encryption. And sometimes service provider takes advantage of your PII, and a totally legit example of this is the credit reference agencies. So basically, they to give you credit, they submit your PII freely to credit reference agencies, and if you were not on file for this specific reference agency, you are on file now, and it's again it's out of your control. And finally, your user passwords always get stolen because service providers sometimes use obsolete crypto, sometimes service providers do not care even to use TLS for authentication, and also phishing attacks like fake login prompts, and many other examples, and we have seen many even during this conference. So what can we do to improve it? So apart from personal training and taking more strict administrative measures to contain private information, to preserve private information securely, we can do something on technical side as well. So we can continuously improve our crypto systems which process this personal identifiable information. So far we have been using only 3 basic building blocks for all crypto systems. These are digital signatures, symmetric encryption, and key agreement. So Another building block which is worth consideration is zero-knowledge protocols, or zero-knowledge proofs, or zero-knowledge algorithms. They all refer to the same thing. So what is a zero-knowledge proof is, it's a method where one party, which we will call the prover, will try to prove to another party, which we will call the verifier, that some specific statement is true. And what it makes zero-knowledge is that by doing this, he will only prove, the verifier will only know whether the statement is true without receiving any other information regarding the proof. Like a counterexample of this, let's say you are authenticating to a website and you use a password to authenticate to a website. So to prove to the website owner or the server you know the password, you actually need to send the password to the server. So basically by proving you know the password, you actually leak the password. So that's where zero-knowledge proofs come. They try to avoid this scenario. And so zero-knowledge proofs are best described by having three properties. The first property is completeness. So which means basically if the statement you are trying to prove is true, the honest prover can convince the honest verifier that the statement is indeed true. The soundness property means that if the statement is false, so no cheating prover can convince the honest verifier that it's true. And these first two properties, they form a broader concept of proofs, which are called interactive proof systems. And actually, we use those proof systems every day. Consider a typical authentication scheme where you authenticate to the server, and server sends you a challenge, which is basically a random value, and you sign this challenge with your private key, and the server verifies this challenge with the public key. So basically, this is a typical example of interactive proof system where you prove the possession of the private key to the server. But what makes zero-knowledge protocols different is the third property, which is zero-knowledge, which is rather complicated to understand. I will try to explain it like this. So zero-knowledge protocols ensure that the proof you are giving to the verifier, if you are the prover, the proof you are giving to the verifier is meaningful only to verifier himself and is only valid at the time of the proof being given. So if the verifier is cheating on you, so he wants to transfer this proof to some third party, he is not able to do that. So it's rather complicated, so let's just check out a classical textbook example of zero-knowledge. You can find this example on Wikipedia. Imagine you have this cave with a weird form, and the cave has a magic door inside, and this door can be opened by saying some magic word. And we have a prover and verifier. The prover wants to prove to the verifier she indeed knows this magic word in a zero-knowledge way. So how can they do that? In step one, the prover will choose randomly a path and enter the cave. The verifier will not know which path did the prover choose. So for example, here the prover chooses path B and enters the cave. Then in second step, the verifier enters the cave and randomly chooses any path as he likes. So let's say in this example, the verifier chooses path A. And so in third step, the prover has to reliably appear on the path which verifier have chosen before. So in this specific case, the prover will use his knowledge of the magic word to open the door and appear on path A, where he entered the path B. So this is how completeness property works now. So the prover has proved to the verifier that she indeed knows the magic word. But there is a problem in this protocol that imagine that in first step, the prover does not indeed know the magic word, and she chooses path A, and the verifier also chooses path A. So in this case, the prover reliably appears on path A, but without even using the magic word, without even knowing the magic word. So this time the prover cheated. So this is a problem for this protocol. There is a cheat probability, and in this case, the cheat probability is 50%. So who needs to use such protocol where you can cheat the verifier with 50% success, right? So the way how it's usually being solved is that you can repeat this protocol several times, and assuming that each round of the protocol is independent, the verifier can ask the prover to do the protocol several times until he indeed is convinced that that prover is not cheating himself. So although there is a small cheat probability, the verifier can make it as small as possible. So in this example, if we repeat the protocol 128 times, we can make it secure as AS. So this is all good, but this is a very simple textbook example. More real-world use cases require more complex protocols, and this notion of repeating the protocol several times is not as good. So there is a very good zero-knowledge protocol, which is called Socialist millionaire. So it's basically it describes a problem where two millionaires want to check whether their wealth is equal without disclosing the exact amount of money each one of them have. So let's see how it works in briefly. Assuming we have two millionaires, and let's call their wealth a secret value. So each of them has some kind of a secret value, X and Y, and they both want to check whether X equals Y. So what they do is they do several round trips of communication. It basically starts as a plain Diffie-Hellman. So they do a simple Diffie-Hellman key exchange, then they do some kind of a signature exchange, and finally they do another exchange of intermediate values. And the final stage of the protocol, they check this equation, and if the equation holds, the cryptography, the math which is used in the protocol reliably states that X is equal to Y. So if you want to follow the math, the low-level math here, so if you unwind the last statement, you will see something like this. And the key point here is this term that if X is equals Y, so this second term will be 0 and the equation will hold. So basically why Socialist millionaire is a better protocol, because it can be easily used to check whether two parties possess the same secret. So you can verify passwords in a zero-knowledge way without actually conveying any password information to the peer. And unlike other zero-knowledge protocols, this protocol is symmetric. So here both parties are provers and verifiers at the same time. And also it has some useful properties that a passive eavesdropper on the communication channel cannot know the protocol outcome. MITM also cannot do better than the passive eavesdropper except mounting a denial of service attack by disrupting the communication channel. So Socialist millionaire is MITM protected inherently. And this is an important feature that even if one of the parties is dishonest, he learns nothing except the protocol outcome. So he learns nothing about the value of the password of the other peer. And why this protocol is more useful in the real case, you do not have to repeat it several times to prevent cheating of the other party. So you have to run the protocol only once and you get a reliable result. And also this protocol is adopted already in open source software, so it's part of everyone's favorite off-the-record messaging, and it's used there to verify keys and protect your messages from man-in-the-middle attack when you send encrypted text. So I would like to repeat that the key point, what makes zero-knowledge protocols are different from other security schemes, that most security schemes are trying to protect communication from MITM attack, but zero-knowledge protocols go further than that. They protect from MITM as well as they allow one of the communicating peers to behave badly, to be malicious. So they provide higher security guarantees than other security schemes. So as I was saying, Socialist Millionaire is adopted in off-the-record messaging, and when I started looking at it, I would like to adopt it in many other useful systems out there. But there was one problem. The protocol implemented in OTR uses 1536-bit prime group calculations. But if you remember last year, we have logjam, which the authors of the logjam state that 520-bit prime fields are already broken. They have shown that. You can use even their special Twitter bot to crack 520-bit prime fields. They also suspect that 1024-bit fields are probably broken by state-level adversaries. So, and if you come to think of it, 1536-bit is not that far from 1024. So even though it might be secure now, it will be surely be broken in a couple of years. So, what we did is to improve the Socialist Millionaire, we just moved it to elliptic curves. And you move a protocol to elliptic curves, what you need to do is you need to choose a good curve to use. So NIST curves are also questionable, as their security is questionable. Also, there is a risk of some patent issues by using NIST curves. So the obvious example here was to use ED25519, which is a state-of-the-art curve by Daniel Bernstein, and it has some good properties. So protocol implemented with this curve has more security features. It's protected from timing attacks. It's faster. Since we moved all the calculations to elliptic curve domain, it has much smaller footprint because elliptic curve values are smaller than prime field calculations. We also added many high-level languages. So if you would like to use the Socialist Millionaire application, you have a variety of choice, but Python, Go, Java, Ruby, whatever you can think of. If you see that your favorite language is not implemented, drop me a note, we'll try to add it. And it has also a simple API, so we implemented the Socialist Millionaire protocol as part of open source library called Themis. It's on GitHub, you can check it, clone it, and use it or improve as you like. So what are the possible use cases of Socialist Millionaire protocol application? So anyone could tell me what's wrong with this slide? Yes. So no HTTPS, authentication over plain HTTP. So security-aware users nowadays, if they see such login, they will never enter their password there. But if we implement, and we actually implemented a prototype HTTP authentication with Socialist Millionaire, it's totally legitimate. So since Socialist Millionaire by itself is protected from MITM, you may use plain HTTP to authenticate yourself to a website with no risk. And even though also if this page will be spoofed by some kind of a third party, malicious third party, they will still get nothing because of the zero-knowledge guarantee of Socialist Millionaire. Another personal use case, actually taken from my personal experience. Let's say you're a playing guy and you want a credit card, and you go to, and you're new to the country, so apparently credit reference agency at this specific country does not have you on record. So you apply for a credit card, you submit your PII to bank. Bank asks whether the credit reference agency has kind of a credit file on you. So bank submits PII to credit reference agency. The credit reference agency replies, oh no, we don't have this guy on the file. Then the bank gets a decision to deny the credit card. And actually you've lost, you didn't receive the credit card, and your PII was leaked to credit reference agency, so it's not fair. So how can we improve that? When I communicate this problem to other developers, they say, oh, we know what to do. We will do a system where we don't send the actual PII, we will send the hash of the PII. So if the credit reference agency does not have you on file, it cannot compute the hash. So basically, it will return nothing, and by receiving the hash of your PII, is they cannot unroll the hash and get your PI because hash functions are considered to be secure. And they make this decision because it's how passwords are compared in operating system. When you log into the operating system, it's how passwords are compared currently on HTTP. But passwords in PI is different because PI is essentially as a unique identifier which identifies you as an individual. So basically, if you apply 2 times from different banks, still the credit reference agency will have this unique identifier because everybody forgets that a hash of the unique identifier is another unique identifier. So basically, how much time you can hash the PI, you will still receive a PI. So it doesn't work this way. So an obvious choice is to try to use Socialist Millionaire here. So if we replace the last step with Socialist Millionaire, the credit reference agency is getting nothing if they did not have you previously on file. So that might solve some issues. Okay, and the last section, when we all did this, we submitted a paper online, and we started to receive feedback from crypto community, and half of the feedback was like negative because they say the protocol is too complex. Why do we need it? Well, we have Pake. Pake now is another very popular protocol which is being adopted on the intranet. It's Pake states for password authentication key exchange, E for exchange, agreement, does not matter. So why it seems it's better than Socialist Millionaire is because Pake requires only 1 round trip, when we remember that Socialist Millionaire requires 3 round trips to securely compare with password. It's simpler, so requires much less asymmetric cryptographical computations, which are rather expensive in terms of protocol CPU cycles. It's easier to implement, and it also negotiates a secret key as part of the protocol, which you can later use for encryption between the 2 peers. So I did some research on Pake and whether it's really applicable. So here I will present some results of this research. So as a reference, there are different variations of Pake protocol. I took the most widespread one, which is called Pake 2, which is currently being drafted for RFC and is already adopted by Google in Boring SSL. And here are the results. This is how basically Pake 2 works. So it's a slightly modified version of the Diffie-Hellman protocol, where you just mix the secret information to the negotiated key. So assuming you have 2 peers which would like to negotiate a shared secret and shared key, and they both know some secret value W, they can execute this protocol with 1 round trip and get a shared key and to communicate securely, which is kind of a same as a Socialist Millionaire, but not quite. So after doing some research, one of the issues which were described by crypto community is that Pake is much, much faster. But because it's simpler, it requires only 1 round trip. But in fact, if you take a more detailed look at the protocol, the outcome of the Pake 2 protocol is a negotiated key. But there is no way a peer knows that the other party negotiated the same key. So if you like to compare apples to apples, so you need another round of the protocol of key confirmation. So actually, if we consider Pake 2 in authentication scenario, it will become 2 round trip protocol and not 1 round trip. So it's still less than Socialist Millionaire, which is 3 round trip, but still it's not that much faster at the end. Yeah, then we did a pure performance analysis. So we took 2 implementation in C. one of SPAKE2 and one is for Socialist Millionaire. It ended up that Socialist Millionaire is only 20 times slower, so it's not 1,000 times, it's not 1,000,000 times, it's only 20 times slower, which is probably a relatively low price if you're willing to pay for high security guarantees and zero-knowledge properties which Socialist Millionaire can provide. Also, this result is more relevant to academia. In real-world case, when we go and ask people to adopt a certain solution, they surely ask for some high-level languages. So nobody will use C anymore nowadays, so they always ask for Python, Java, Ruby, Go, and whatever language. And it's typical, if you use high-level languages, SMP ends up only 3 times slower than SPAKE2, because most of the processing time is spent on network communication and runtime support than on actually protocol computation. So in the end, SMP is slower, but not much slower. It's a little bit slower than SPAKE2, but it provides higher security guarantees. So another response from crypto community was that SPAKE is better because it negotiates a security key as part of the protocol outcome, and SMP only checks whether secret values are equal. But apparently, if you take a closer look to SMP again, you will see that it actually does 2 Diffie-Hellman key exchanges before the protocol begins. So if the last equation holds, you will actually get 2 secret keys if you just store these intermediate values, so you have the same functionality as SPAKE. And this brings another very interesting use case for Socialist Millionaire. You can use it to provide automatic key rotations for systems which communicate over encrypted channel over long-lived network connections. So assuming you have 2 distributed systems which communicate securely over key 1, at some point it's a good security practice to rotate the keys, but it's always hard. The key management is always hard. So here you can just use Socialist Millionaire protocol to store those intermediate negotiated keys and just rotate the key. It's very easy and can be fully automated without any human intervention. This is like a combination of every other aspects that crypto community, negative feedback of crypto community provided regarding SMP usage. So I would like to stress out that if you take a closer look at SPAKE2 or any PAKE protocol, PAKE is a key agreement protocol, and it's not a good security practice to use key agreement protocol for authentication at all. So, and because the goal of the key agreement protocols is to negotiate a shared key and not to authenticate your peer. And specifically, PAKE protocol does not even provide the proof that your peer knows the secret. If you take a closer look here, you will see by examining those values that actually SPAKE2 does not use the secret per se in the protocol computation. So to provide an analogy, let's consider that W is some kind of a private key. Then these terms which are used in protocol computation are only public keys. So SPAKE2 provides the proof that your peer knows the public key, which is derived from the secret, not the secret itself. So it's not even, it doesn't even contain the proof that your peer knows the secret. So if I'm an adversary, I can successfully communicate using SPAKE2 by knowing only the public key, which is derived from the original secret value and not the secret value itself. And this may create issue. For example, if you ask some developer to implement SPAKE2 in a secure manner, so secure manner would mean to him that he should zero out all the memory which were used for storing secret values. So eventually he will probably zero out the memory which was used to store W, but if I dump the process memory after the protocol finishes, I can just dump those intermediate public values and use them successfully to communicate with peers. Of course, so there are ways that can improve this protocol in a specific implementation. So you can say that, oh, you should treat the intermediate computational values as secret in themselves. You can just accept the risk that nobody will dump those intermediate computation values, and you can just enforce on implementation level that these values are never persisted in memory. But anyway, you have to somehow deal with it, and this is not specified in the original protocol. So that's why SPAKE is not very suited for authentication cases. On the other hand, Socialist millionaire, in Socialist millionaire, you always use the secret itself in the protocol computation, and all the intermediate parameters are random values with contributions from both parties, so they are meaningless to all other adversaries which may dump the process memory later, and this is also ensured by zero-knowledge property of the protocol. So that's probably it. So takeaways from here that you can use zero-knowledge protocols as another building block to build security-enhanced and privacy-preserving applications. So it's very useful in a scenario when the threat model assumes that one of the communicating parties can be malicious. You can still use, with all the caveats, you can still use SPAKE for most of the cases, but you have to be aware of its caveats. And basically, Socialist millionaire will provide you more security guarantees, although with some small performance penalties. So if for everybody is interested, you can read the paper which describes Socialist millionaire on ECC in more detail, and you can check the code on GitHub and use, pull request, improve, and other things. Thank you. Questions? No questions? Thank you.